Okay, this video is on Chapter 3, Section 1, and the topic is exponential and logistic functions. What you'll learn about in this section: exponential functions and their graphs, the natural base E, logistic functions and their graphs, population models. Why we learn this: exponential and logistic functions model many growth patterns, including the growth of human and animal populations. So let a and b be real number constants. An exponential function in x is a function that can be written in the form f of x equals a times b to the x, where a is non-zero, b is positive, and b is not equal to 1. The constant a is the initial value of f, the value at x equals 0, and b is what we call the base. So determine formulas for exponential function g and h whose values are given in the table below. So here on the left we have some x values, and here in the middle we have function g and its values, its corresponding function values for the given x values, and here we have function h. So let's focus on g for a minute here. As x increases by 1, the values of g are multiplied by a factor of 3. And so we can use that information to write an exponential function for g. If we look at h, the values of h are actually decreasing. They're decreasing by a factor of 1/4. So how do we take that information and write a model? Well, because g is exponential, g of x equals a times b of x, and b is, again, is the base. Because g of 0 equals 4, which we were given, a equals 4. Remember, a is the initial value. That is always the coefficient on the base to the x power. Because g of 1 equals 4 times b to the first, which equals 12, the base is 3. So g of x equals 4 times 3 to the x. And again, if you go back, the common factor from term to term as x increases by 1 is going to be the base. So that's 3 to the x power, again multiplied by our initial condition or our initial value of 4. So this is the exponential model for that data. Now remember, we can't actually multiply 4 times 3 here, because it's 3 to the x power, so we have to keep them separate. If we focus on h for a minute, much the same way as g, our initial value, our value at 0, we had a value of 8, so a is 8. And we notice that the common factor from term to term is 1/4, so that is the base of the exponential function. So the function itself, the entire function, is 8 times 1/4 to the x power. Now, when we talk about exponential functions, a lot of times we talk about exponential growth and decay. For any exponential function f of x, which equals a times b to the x, and any real number x, f of x plus 1 equals b times f of x. What this is saying here is it's saying that this value, this function value here, the next function value when we add 1 to x, is basically built off of the previous value, f of x, and we just find it by multiplying that function value by the base. And we kind of saw that in the patterns that we were looking at just a moment ago. So if a is greater than 0 and b is greater than 1, the function f is increasing and is an exponential growth function. The base b is its growth factor. If a is greater than 0 and b is less than 1, the function f is decreasing and is an exponential decay function. The base b is its decay factor. So let's take a look at some examples of transformation of exponential functions. Describe how to transform the graph of f of x equals 2 to the x into the graph of each function, and then graph each function. So if we look at a, g of x, what's changing here is we're subtracting 1 from the inputs. So when we see that, when we are subtracting 1 or adding a value, any value, to the inputs of the function, we know that that's a translation right or left. If you look at b, we're changing the sign of the inputs, okay, from f. And that's always going to involve a reflection anytime we're changing sign of inputs or outputs. And then k, part c here, k of x, we're taking the function f 3 times 2 to the x. And anytime we multiply a function by some value, that's going to involve a stretch or a compression. So just by looking at these functions and how they're different from f, we should be able to identify at least what's going to happen to the graph. And then we can actually look at the graphs to see what they look like. So here in A, we talked about we got a translation. When we subtract 1 from our inputs, that's actually a translation to the right, which is usually the most confusing translation. So here you can see the dashed curve is 2 to the x, and then the solid black curve is 2 to the x minus 1. You can see they give you two reference points here that are both translated 1 unit to the right. On B, again, the dashed curve is 2 to the x power. When we change the sign of our inputs, this gives us a reflection across the y-axis. So you can see here our reference point is this point here, and it is reflected across the y-axis to this value over here, and every other point on the dashed curve will be reflected as well. And in part C, we had k of x equals 3 times 2 to the x, and we talked about how multiplying a function by some constant value gives us a stretch or a compression. And since 3 is greater than 1, we know that it's going to be a stretch. So all the function values are increased by a factor of 3 for each unique x value. So here we go from 2 to the x, 3 times 2 to the x. Okay, when x is 0, 2 to the 0 is 1. When x is 0, 3 times 2 to the 0 is 3. So that's these two values here. Now we talk about the natural base e. You know, an exponential function can have many bases, but the common base that we look at a lot of times is base e. And this is the definition of e. E is defined to be the limit as x goes to infinity of this expression, the quantity 1 plus 1 over x, all of that to the x power. The limit of that is defined to be the number e. So if you just stop for a moment and think about that, as x goes to infinity, we're taking 1 and we're adding a fraction to it. And as x goes to infinity, think about what's happening to the value of this fraction. As x gets larger and larger and larger, this value, the overall value of this fraction, is getting smaller and smaller and smaller. So we're taking 1 plus some very small number, and then we're taking that to a very large power. So, you know, think about how that might play out. And let's take a look at some examples here. So here I have some screenshots from a calculator that just show us what happens as we take x values 1, 2, 3, and so on. So here we have an x value of 1, and the value of that expression is 2. When we take an x value of 2, the value of that expression is 2.25. When x is 3, the value of that expression is 2.37037. So you can see it's increasing. But what you'll notice is as we go from 4 to 5 to 6, the value of that expression continues to increase, but it is increasing at a slower rate. 7, 8, 9, increasing at a slower rate. And then in this last screenshot here, I took values of x values of 15, 150, and 1500. And you can see those values are still increasing, again, each time at a slightly lesser rate, if you will. So what does that mean? Well, it means that there is a limit to this value. So if I use my calculator to calculate the limit as x goes to infinity of that expression, I get a value of 2.7182, and so on and so on and so on. Well, if I take my calculator out and I just look at the decimal approximation of e, it is 2.71828, and so on and so on and so on. So this expression here, this is the definition of e. This is how the value of e is computed. So any exponential function f of x that equals a times b to the x can be written as f of x equals a times e to the kx for any appropriately chosen real number constant k. If a is greater than 0 and k is greater than 0, f of x equals a times e to the kx is an exponential growth function. And if a is greater than 0 and k is less than 0, then f of x equals a times e to the kx is an exponential decay function. So this is just a variation of the definition of exponential growth and decay that we looked at a few moments ago, now just involving the base e. So let's take a look at the graphs. Here's the graph of an exponential growth function on the left. Okay, we are going to have a value of 0, 1. Okay, anytime we have b to the x, this common point 0, 1 will always be on that curve. And if we look at the decay, this time where k is less than 0, so k is a negative value. So really, if k is negative, then really this is going to be 1 over e to the x. So again, we could look at transformations of exponential functions, and these are going to work exactly the same way as they would with other bases of exponential functions. These are just base e. So here we have g, h, and k. Think about what these transformations are going to look like, transformations of the function e to the x. Think about what these will look like, and when you're ready, you can play the video. So here is our transformation of e to the x, where g of x equals e to the x plus 2. Again, we're adding 2 to the input value, so this is going to involve a translation to the left 2 units. Okay, so all the points of this is e to the x, and over here this is e to the x plus 2. So all values are translated left 2 units. So here we have the transformation of e to the x into negative e to the x. So here is e to the x, and here is negative e to the x. See, this time we are taking the function values and we are changing the sign of the function values, so this gives us a reflection across the x-axis. The previous example that we looked at, we were changing the sign of the input values, and that gave us a translation across the y-axis. So we have to know what gives us a translation across the x-axis, what gives us a translation across the y-axis. And here we have a translation down 1 unit. We are taking the function e to the x, and our new function k of x, we are subtracting 1 from those function values, so everything gets translated down 1 unit. Okay, so when we talk about exponential functions, and we start talking about exponential relationships in the real world, we have to consider this function called the logistic growth function. And here's how the logistic growth function is defined. Let a, b, and c, and k be positive constants with b less than 1. A logistic growth function in x is a function that can be written in the form f of x equals some value c over 1 plus a times b to the x, or f of x equals c over 1 plus a times e to the negative kx, where the constant c is the limit to growth. So like I mentioned, in the real world, with limited resources, exponential growth cannot continue indefinitely. Exponential growth may occur in environments where there are a few individuals and plentiful resources. But when the number of individuals becomes large enough, the resources will be depleted, slowing the growth rate. Eventually, the growth rate will plateau or level off. This population size, which represents the maximum population size a particular environment can support, is called the carrying capacity. So if you think about what that says, it kind of makes sense. There are limits to population. Various resources are going to limit the size that a population can have. And so here you see an example of what we call a logistic curve. The first part of the logistic curve here is exponential in nature. Okay? But what happens is, just like the scenario says, we get to a point where things start to level off or plateau, and this logistic curve starts to trend this way. Instead of increasing, the values are still going to increase slightly, but they're not going to increase at the rate that they were before. And you'll notice something interesting happens at about this point here on the graph. One word that we haven't discussed yet, and you will discuss in much greater detail in calculus, is called concavity. See how the exponential growth part of this logistics curve, we call this concave up. What happens is there's a point where that function transitions from a concave up graph to a concave down graph. And there's a lot of interesting information that we can discuss at that point. But there is definitely a change in the behavior of the function at that point. So that's called a logistic function or a logistic model.